Hello, and welcome to this Xilinx Quick Take tutorial focusing on designing with UltraScale Memory IP. It allows you to make MIG I/O changes without needing to re-customize or re-implement the IP. There have been some IP and methodology changes in 2015. Firstly, we've simplified the memory interface quite a bit, and we've enabled the PHY-only implementation without the memory controller. We provided a faster BFM model for simulation, and most importantly, we've centralized the I/O planning tasks, moved it out of the IP and into the Vivado I/O planner with the rest of the design. This gives you some specific advantages. It allows you to target different devices with the IP without re-customizing the IP, and it enables simultaneous I/O planning for multiple memory controllers. This also makes the behavior consistent with other IP in the Xilinx catalog. The agenda for the demonstration is we'll briefly review the 2014.4 memory I/O planning flow, and then we'll review the new memory IP customization wizard. We'll configure an IP and we'll create an example design, and then we'll open up the elaborated design or the synthesized design and use the new memory byte planner. We'll manually modify some memory I/O ports, run the DRC to ensure compliance, and then we'll save those constraints to the top-level constraint file. I'll then show you how you can create an example design with multiple memory controllers. Again, we'll use the byte planner to plan multiple controllers. We'll use the autoplace capabilities to target specific I/O banks for various controllers. I'll show you how to configure ports, and then we'll implement the physical layer, or PHY, during op design. And then we'll examine the implementation results and the floor plan created. And finally, we'll talk about how you can migrate your memory IP I/Os from your example design to your real design or back again. Let's go ahead and open up 2014.4. In all releases prior to 2015, the I/O assignment for the memory controller IP was done as a part of customizing the IP itself. As you can see here in this 2014.4 version, the customization wizard had two tabs for pin planning. It had the bank planning here where you could select your byte lanes for the various pin groups. And it also had a MIG I/O planner, which was a trimmed down version of the Vivado pin planning environment for pin planning the MIG IP specific I/Os only. You also had no insight into the other I/O ports in the design. When the output products for the IP were generated, an IP specific constraints file contains all the physical constraints, including the package pin lock constraints for the IP I/Os. This essentially locks the IP with this group of I/Os. Any modification to the I/Os or any retargeting of the IP required regeneration of the output products, which made seemingly simple printed circuit board pin swaps very cumbersome. In 2015.1, the MIG customization wizard for UltraScale has been simplified and improved quite a bit. There's now a simple pull down to select the type of memory you'd like to configure. There's an option to generate the physical layer or PHY layer only for using external controllers. And notice now, if I select a memory device interface speed that's faster than the allowable range, it turns red and does not allow me to set it. So there's some checking going on there. And another new handy feature is the ability to import a custom parts data file if you have a custom memory device that may have a deeper part or what have you. And I've selected the CSV parts file for my custom part. And you can get sample CSV files under the link provided here. Notice there's some configuration capabilities for the memory part, the memory options. And if I go to the Advanced tab, one of the things I can do is enable debug signals for the controller. There is a separate video on using this capability titled Vivado Hardware Manager for UltraScale Memory IP. And then below that, you'll see simulation options. We've recently introduced a bus functional simulation model for the memory controller, which will greatly speed up your simulation times. You can select the BFM or the Unisim, which will do the more elaborate simulation. And there's some clocking options below. And one of the biggest changes you'll notice is the byte planner and the MIG I/O planner have both been removed. We've put a note in here to tell people that there is a new methodology for assigning memory controller I/Os in 2015. There are also links to the appropriate videos and documentation that describe this process. If you're migrating from the 2014 release, There is a migration video which walks you through the process of migrating your scoped MIG IP I/O constraints to the top-level constraint files in 2015.1. And the last tab contains a link to the MIG design checklist. Performing this checklist is recommended for people designing memory interfaces. The checklist is basically a series of questions at each stage of the design of the memory interface with appropriate suggestions and links to more information about these questions. As you can see from the bottom tabs, there's a separate checklist for each type of memory. I'll give my IP interface a name, in this case DDR3, and click OK to generate the IP. I'm presented with the Generate Output Products dialog, which allows me to either select Global to synthesize the IP RTL source files along with the rest of the design, or Out of Context, which will synthesize the IP standalone, and then use that netlister in implementation, which can help speed up synthesis times. I'll choose Out of Context, and you'll see that a run is started for this IP. Once it's complete, all the output products are available to me in the sources view, and if I look down inside at the constraint file, notice the physical constraints now for the memory IP do not have any package pins associated with them. There are I/O standards and output impedance and so forth, which will help you do the pin planning for the memory interface, but no physical locations have been decided in the IP. That's all going to be done in the Vivado pin planning environment, which we'll go through now. To do memory I/O pin planning, you must have the memory IP instantiated in a design. The easiest way to do that is to open up an example design. A separate project is created with this IP instantiated in it, along with a test pattern generator for simulation. If I open up the top-level constraint file that was created with the example project, notice there are package pins assigned. When you create an example design, a default I/O pin placement is selected for you, so the design will go straight through implementation. If you were instantiating this IP in your design, you would not get a default pin placement. If I want to modify those defaults, I can do it in one of two places. I can open up the elaborated design, which is pre-synthesized elaborated RTL, and do my pin planning there, or I can run synthesis and open up the synthesized design. Let's open up the elaborated design. And when the design is open, you're presented with a schematic, and notice you can see the memory device and the test pattern generator off to the left here. To do pin planning, I'm going to open up the I/O planning view layout, which will basically display views that are more appropriate for I/O pin planning, as you can see here with the package view. Down in the I/O ports view, you'll notice that there's a I/O port interface that's been created that contains all of the ports associated with my memory controller. This is very handy when you're doing design. You can select or place or manipulate all of the memory controller I/O ports by selecting this folder. You'll notice as well in the banner, it says that this design does contain memory interfaces, and that you should select this button to launch the memory byte planner. But before I do that, I'm going to take advantage of another Vivado pin planning feature and split the views here so that I can see both the device view and the package view simultaneously while I'm doing pin planning. The byte planner is very similar to what was inside the IP in prior releases, but it does have some very nice advantages. Notice as I select either byte groups or I/O banks, they're also selected for me in the package view and in the device view. This visual reference is very helpful when trying to select the proper locations for your memory interfaces. So visually seeing where they are on the device will greatly aid the selection process. For example, I'd probably want to put my data pins here on the outside of the device for easier printed circuit board routing. And you can use the pull-down menu to select the pin groups that you'd like to assign to that byte lane. And notice that as I create violations, they're displayed in red, telling me I've got an illegal condition while I move this interface from one I/O bank to the next. There's also an active DRC link at the top of the dialog, which you can click on the link to tell you what the issues are at any particular point during your pin planning. And notice that once I move the entire interface, the red goes away. And you can see here that the interface is moved into the I/O bank next to it. And that's how you assign pin groups to the various byte lanes within the device. We're going to cover some of the advanced features of the byte planner in a moment, but first I want to explain how to do manual manipulations of I/O ports. Manual port modification can be done in two places, in the I/O ports view and in the package pins view. Both of these views offer a lot of options for how you can sort and filter and display the data. There's a flattening button that'll present a flat list of the entire list of ports. I can sort the list by clicking on any of the top columns. To do manual manipulation, I can click into the site column here and select or enter a new pin location for that port. In this case, I'll choose to swap two ports around within the same bank. Notice that when I enter a port name that's already assigned, it asks me if I want to unassign it to move on. So it does not automatically unassign if I accidentally type the wrong thing into a field. So that's how you can modify port assignments within the I/O ports view. In the package pins view, it displays the pins of the device and the I/O signal names that are attached to them. Notice that the pins are also organized into byte groups, so you can see the pins that are inside the byte groups to aid in assignment. In this case, you can use the pull down to select a new signal name to perform the same operation. It's really user preference on which window they'd like to use. As always, when assigning or modifying I/O ports, especially with the memory ports, you should always run the report DRC command prior to moving on in the flow. And as you can see here, I'm only presented with one warning saying my device configuration parameters are not set. I'll ignore those for now. The next thing I want to do is write these constraints into my constraints file. All of the changes and modifications I've made so far are strictly in memory. So to do that, I'll use the save constraints command, and I'm presented with some options on whether I want to write these constraints into a new file or use the existing file that I have in the top level. I'll elect to use my existing top level file. And notice when I open it, it contains all the package pins and I/O standard constraints for the memory IP. I could easily go on and run synthesis and implementation on this design and run through the flow. I'm going to now demonstrate some of the more advanced features. Sometimes you need to create an example design or to do memory pin planning with more than one memory controller. As you can see here, I've got a DDR3 and a DDR4 controller in this Manage IP project. In 2015, we're offering a Tickle app through the Tickle store that will enable you to create an example design that contains more than one IP. So inside of the Design Utilities bundle, you can see a command called Create Combined MIG-IO Design. I'm going to install this and run the command. The command is asking for a project name for the new project to create and a list of IP to put into it. In this case, I'll just use get IPs, which will include all of the IP in the design, in this case, the DDR3 and DDR4 IP. The new project is created with both of the IP instantiated. This example design is to be used for MIG-IO planning only. There is no test bench generated for the various IP. I'll go ahead and open up the elaborated design, and you can see with this design, no default pin placement is provided for you. You're starting from a clean slate. To change things up a bit, I'm going to run synthesis on the design and open up the synthesized design for pin planning. And in the I/O ports view, I can see both of my memory interfaces. And when I use the pull down, I can see both of the controllers' pin groups available to me for selection. This was never possible in previous versions of software. I can simultaneously pin plan multiple controllers in one design. And here you can see I've manually assigned my DDR3 interface. I could do the same for the DDR4, but let's show off some of the autoplace capabilities. When I select the autoplace button, I'm presented with a choice whether I want to autoplace all the controllers or just the DDR3 or DDR4. In this case, I'll select the DDR4, and I'm then presented with a selection of which banks I want to autoplace this controller in. Again, this is a new feature that allows you to target specific banks for your I/O controllers rather than have to manually select the byte groups for each pin group. And you'll see the interface has been auto-placed into the banks that I selected. Now with this example design, there are some additional status ports and the reset ports that also need to be placed. I'm going to use the traditional Vivado I/O placement tool to place the non-memory I/Os. And notice it's done that for me. Now when I re-invoke the memory byte planner, notice some of the banks have yellow circles with exclamation points in them. If I hover my cursor over, it's telling me that there are non-MIG ports assigned to that I/O bank. Because of this, you will not be able to do any assignments of any MIG ports into banks that already have non-MIG pins assigned to them. One way to start with a clean slate for doing memory I/O assignment is to select all ports in the I/O ports view and use the unplace command, which will unplace all of the ports in the design. Notice now when I bring the memory byte planner back up, it's a clean slate. And I'll just go ahead and use the auto placer here to place both controllers simultaneously. And notice it's done that. And when I select the I/O port interfaces in the I/O ports view, you can see where it's placed them. I want to make sure I report the DRCs to see if I've got a legal placement. Oh, and notice that I do still have some unplaced ports and some default I/O standards. Again, these are the status-related ports that I just unplaced a moment ago. I do want to show you a handy trick when you have to assign I/O standards to multiple ports. You can flatten the I/O ports list and sort by I/O standards, and notice the defaults are here at the top. If I select them all, I can use the configure I/O ports command to select a I/O standard for all of them simultaneously. Any ports left with a default selection will not pass bitstream, so you do have to manually assign I/O standards to every port. I'll now place those ports using the place I/O ports into an I/O bank and rerun DRC. I get that same warning complaining about my device configuration, so I'll go ahead and set that using the edit device properties command. I'll set my configuration voltage and bank voltage selection and rerun DRC. Notice now I have no violations. I'll save all my assignments to a new top-level constraint file called IOs, as you see here. And now I'll elect to rerun synthesis and implementation to implement the design with my newly selected ports. Now, the one new caveat with this memory I/O flow is that the PHY needs to be implemented after the IOs have been selected. So the first step to implementing the design is running opdesign. And in phase 1 of opdesign, you'll notice a new command which says synthesize and generate MIG cores. This step can take a few minutes for each core the first time through. And to demonstrate some additional features, I'll open another design with 4 memory controllers. And here you'll notice the 4 memory controllers in the sources view. This design has already been completed through place and route, so I'll open up the implemented design. Here you can clearly see the P blocks that were created for each of the memory controllers. You'll notice here in the byte planner that these 2 memory interfaces have actually shared an I/O bank. So I've got pin groups from multiple memory controllers planned into the same I/O bank. And you can see that here when I've highlighted the bank. Notice the P blocks have actually been created to split that I/O bank to accommodate both memory controllers. The P blocks have also been reduced in size to try to condense the memory controllers to increase performance. So that's it. That's the new methodology for doing I/O pin planning for memory controllers in UltraScale. And the last thing I want to show you is how to migrate your memory IOs from your example design into your real design or back again. Here I've got the example design open for this DDR3. So as you can see in the package view, the ports are placed, and I'm going to go to the Tickle console and use the write xtc-cell command and give it the name of the memory instance and an output file. And this is going to write scoped constraints to the IP module into that file. I'll then open up my real design. As you can see here it's my design with 2 memory controllers in it to mimic a real design. And I'll go to the Tickle console and use the read xtc-cell. And notice it is a different instance name. And I'll import the file. And it populates the ports per that memory instance in my design. And then when I use the save constraints command, it will migrate those module level port names up to whatever top level port names you have in your design. In this case, they happen to be the same because I use the same example design creation methods, but these ports could differ. They'll inherit the top level ports, and you're good to go. Now notice here it's added an additional constraint file to my constraint set when I use the read xtc command. There is an option called no add that will simply read the constraints into memory, and then when you do the save, it writes them to your target constraint file, which in this case is my top level file. And notice all my constraints are in one file. So it's your choice in how you want to manage your IP I/O constraints. So that's it. That's the new memory I/O planning methodology for UltraScale IP in 2015. So in summary, in 2015, we've simplified the memory customization wizard. We provided faster simulation models for memory IP, and we centralized the I/O planning task to allow you to make I/O changes without needing to re-implement the design and to target different devices, as well as be able to I/O plan for multiple memory controllers simultaneously. And this really makes the memory controllers now behave consistently with other IP in the Xilinx catalog. Thank you very much for your time.